Entonces, we have said that, we have said that this was just an experience that we developed some years ago, applying finite elements in order to solve this problem, okay? And these were the results. Okay, now let's do an example here, okay? So, before that, as a summary, okay? Let's consider that we're going to solve, okay, for each one of these strips, okay, we can solve and calculate the force. Remember, well, this is incorrect, okay? This is not differential, okay? Okay, so this is that. Okay, so this is multiplied by dx, and this is dfd. Okay, so this is the differential of the force, and that's equal to force per unit length times length. So please correct in your class notes. Okay, this is incorrect. Okay, now this fd integrated along the length of the ship can produce the force. That's what we need in our equation. Okay, so in this case, I'm talking about pure heave. Okay, so the ship moves vertically, okay, with no rotation. Okay, and in this case, we know that there is going to be a term proportional to the acceleration, which opposes the acceleration, and that's the added mass. This is per unit length multiplied by dx, and we integrate, and that gives us the total force. Similarly for the damping, okay? And now, remember that we did this expansion, okay, the Taylor series expansion. So this here is just the partial of z divided by eta 3 dot, okay? Similarly for this one, okay? Now, okay, so we have this negative here. We can move this negative to the other hand side, and this is what we obtain. And you see immediately that this is added mass, total added mass. Ms. Lopez, that's what I was asking you, okay? So every time in this class or in general in ship dynamics, we have a large letter, that means that it's a total. And when we express that in a little, that's per unit length in general, okay? Similarly for the damping. But now we could do something similar for the pitch, okay? So in this case, we have to be careful because what we do is we give a unit rotation. So this is eta 5. Okay, so this rotation is positive, right? That means that this point moves downward a distance equal to eta x times eta 5. Remember, eta 5 is radians, right? So if this is the vertical displacement, you could differentiate that with respect to time, and that's the velocity, and that's the acceleration, right? So if this moves vertically, okay, that's similar. This is the same force which is developed here against this velocity, against this acceleration. So we could use the same A33 in B33 in order to calculate the moment. This is what we obtain, okay? So remember that to calculate moment, we need to multiply the force times an arm. And the arm is the distance from here to here. So we have 1x, which is multiplied by eta 5 to calculate displacement. And we multiply that by x again to calculate moment. So we have x squared, and that's what the reason why you have it here and here. Okay, but you can see that immediately that we use the same A33 as for the heave problem. Okay, and then, okay, we can consider that the fact that even if you go up, okay, since the bow or the forward portion of the hull is different as the aft. Okay, if we consider both the forward and aft parts, you're going to have a net moment. Okay, so that's what you have here. Okay, here. Okay, so these two hydrodynamic derivatives, okay, couple. This is Z because of a unit rotational acceleration. And this is moment because a unit vertical acceleration. And that's because the bow or the forward part of the hull is different than the aft portion of the hull. So every time you do that, you have a net moment which tries to make you rotate. Every time you rotate, you have a net force which makes you try to go up. Okay, so that means that the two problems, heave and pitch, will always have to be solved coupled. Okay, that's the summary of the hydrodynamic coefficients. So we have hydrostatic, hydrodynamics, we have the inertial terms. The only term that is missing, well, we are not going to do it today because I don't think we're going to have time, is the excitation that comes after this. Okay? So how to calculate these partial derivatives? Okay, this little A33 and then integrate it. Okay, so that's what we're going to show with an example. Okay, so let's suppose that we have a ramp like this one here, and this is something, a cylindrical float. Okay, it's floating, and you see that it is as a cylindrical shape. Okay, so this diameter here is 2 meters. This distance from the pin to this center, it's 4. And the length of the float, that's this dimension, okay? This dimension from here to here, that's again 4 meters, okay? So we're going to represent this with a model in order to calculate then the oscillation, okay? So we're going to model like this, okay? If you push this downwards, okay, that means that you are going to increase, okay? You're going to increase the buoyancy. So that means that you're trying to put the extra buoyancy will try to bring you up. If you pull this up, you lose buoyancy. So the weight is winning and they will push you downwards. So you're going to have a restoring effect as a spring if the displacement are small. Okay, we can neglect everything else, so we can say that this is this. Here we have a mass, and here we have a spring in there. So that's K, this mass, that's it. So the spring will represent the hydrostatic effect, okay? And the mass here, we have to call it an effective mass. Why? Because in here, we're gonna have a hydrodynamic effect. Okay, and the hydrodynamic effect means that you're going to have to include, we are going to have to include added mass and damping coefficient. Okay. Questions? No? That's easy. Okay, now let's do it. So this is our free body diagram. So we have something like this. I'm sorry. like this. We assume that this is massless. Here we have a mass. We call it M sub E, effective. We have a spring there. Okay, so let's go in this direction. We call it theta. We call it X. Let's call it Y. In Z, you can see that X, Y, Z is coming outside from the plane. Okay, so this is theta, which depends on time. Okay, so when at a small angle will be like here. So the free body diagram shows you here. So you're going to have a force downward, and this force is going to be what? So it's going to be K times L theta. Okay, for small, let's call it approximately, right? Okay, and this is the mass, effective mass, and this is a point O. And yeah, we have two forces here, but if we take moments with respect to O, we are not going to have any problem with that. So we say summation of moments with respect to O. Remember, this is something that we agree in chapter 1, that if we take a point which is fixed, the easiest, I mean, to understand easily between you and me, we agree. We agreed that we're going to call it O. C or G for the centroid, and P, which is the general point which can move. Okay, so in this case, since O is fixed, okay, we don't need the other term. And this is the inertia with respect to O times the acceleration. Okay, here, I'm sorry, I have to include another force. Okay, we have to include another force. It is a hydrodynamic force. Okay, so okay, we have this. This is the positive. I change color. Let me change color. Okay, so you have the minus KL theta. That's the force, and multiplied by the arm minus hydrodynamic times L, and that's equal to the mass. This is a dry mass times L squared times theta double dot. How do you calculate the hydrodynamic mass? Anybody? Hydrodynamic mass? Ms. Vega, how do you calculate hydrodynamic mass in this case? Ms. Vega, how do you calculate hydrodynamic mass? Ms. Vega, are you there? Vega, hello, wake up. Please, Giovanna. Mr. Galarza, Mr. Íñiguez, how do you calculate hydrodynamic force?
For the difference by the arm.
Listen to my question. Hydrodynamic force. Mr. Íñiguez, tell me, how do you calculate hydrodynamic force? Miss Astudillo, how do you calculate hydrodynamic force on this float?
With the sigma and volume.
Now, what concept comes to your mind in this case?
Mass.
Added mass, yes. So it's going to be added mass times acceleration. How do you calculate the linear acceleration, Miss Astudillo?
And T.
Linear acceleration. What? Sorry?
Acceleration and T.
Sorry, I'm not listening to you. L times. Ms. Lopez, help me out. How do you calculate the acceleration of this end?
Square. ML square.
Beta, beta,
Ah.
beta, double dot. Come on, people. So that's the linear acceleration times the mass, that's the force. And we have considered that it's producing a opposing to this acceleration, right? And we don't forget the L. So let me go to on this side. So we put everything on perspective. There. Cos what? It's going to be K L squared theta equal to 0. Okay. If we had included, maybe we should do it. Maybe we're going to include here. We're going to include here the damping. Mr. Zambrano, help me out. How do you calculate damping here? How do you put this damping moment here? You put it here. Mr. Zambrano, please.
It will be times the velocity.
That's force. That's force, but this is moment. So we need an arm, which is L. So it's going to be B33 times the velocity, which is equal to L theta dot, the arm, and this is opposing. So let me put this on the right-hand side. Please don't write on my screen, people. Come on. So it's going to be B33 L squared theta dot plus K L squared theta equals to 0. Okay, so in this case, natural frequency is simply equal to K L squared over mass times added mass L squared with the damping
Doctor, I
coefficient.
have a question. Just to add the damping coefficient.
I don't understand your question. I'm sorry. Could you repeat your question, please?
In the summatory of the moment,
Yes.
in this equation, just to be add the damping coefficient.
Yeah, because remember, damping means that, for example, let's suppose you go up, right? So you generate a wave like this. And it's sucking you down. So that force is equal to B33 L theta dot. That's the force. You multiply by an arm that will produce a moment.
Thanks. Right.
No problem. No problem. And here we can calculate remember the little gusanito? Do you remember the expression for this? Anybody? It's C over C critical, right? Right? Anybody? The C critical, anybody remembers the C critical?
Two and natural frequency.
Natural frequency.
So this is like an effective, right? Okay, so in this case, C, we have it here. This M is this thing here. So we have B33 the L squared cancels, and we have 2m plus added mass in natural frequency. Okay. So let's calculate now, finally. Let's calculate the natural frequency and all of that. Questions about this, people, so far? No. Okay. Let me go back here. Here. Okay, now, to calculate not added mass, okay, per unit length, A33, little A33, we need a frequency. But we want to calculate frequency, so we are in a vicious circle. How do we do? How do you propose to do it? Isidro, what do you propose?
We can assume a value for the frequency.
Yes. So we can assume a value for the frequency, calculate added mass, with the added mass, calculate natural frequency, and if the assumed value is quite different from the calculated value, we have to repeat the calculation. Okay, so, okay, let's do it. So let's assume an omega squared. Yes.
We assume a value for the natural frequency, and then we calculate the added mass, and then we calculate the natural frequency.
Yeah.
And we have to compare both values, the assumed natural frequency with the calculated, or
yeah.
How we know that that value is that value that we assume is correct.
See, the only thing that you can do is you're saying is that this expression here, if this is correct, if this is I'm sorry, this is a correct model, right? This is a natural frequency. But the problem is that this parameter here, added mass, depends on the frequency. So what you have to do is you have to assume the frequency, calculate this, and with this value, calculate omega. If this is exactly the same as the one that you assume to calculate added mass, you are correct, because this is the expression for the natural frequency when this is the correct model for this system. So once those two are the same, you are fine. Okay.
Okay, thank you.
So let's simply for this calculation, let's assume a value for omega squared b over 2g. Okay, I have an exercise here with a value of 0.4. Okay. So, oh man, I'm in trouble here because I don't have the scale. Let me go back. So you can see that the increment is 0.2. Increments in the scale is 0.2. So we are 0.4. Let's start at 0.4. Okay, so we are in on this line. Okay. Before we have to select this one here. I'm sorry, I chose, for some reason I made a mistake. This is incorrect, but anyway. So beta n, that, Mr. Barba, do you remember what was beta n equal to? Beta n, Mr. Barba?
In this
The area. What's the area in this case?
in this case is 1.
No, come on.
L is up. R
It's P
E
R
R
squared over 2.
over 2.
Okay, so it's P R0 squared. That's the area of the full circle. But we have only half of that. Okay, now, then we have to divide it by the area of this rectangle. What's the area of this rectangle?
BR sub 0.
It's 2R0. That's the distance from here to here. And multiply by R0. So we cross this, cross that. So it's equal to pi over 4. So it's about 0.8. Unfortunately, I brought the wrong curve. Okay, you can correct that at home. What else? We need a curve for this. So we need the ratio Bn over T. How much is Bn over 2? Bn over T. Miss Lopez, please help us. What is Bn over T in this case? Miss Lopez, can you hear me?
Yes. Wait. Um, I don't understand.
How much is B? How much is B? How much is B?
Row.
From here,
To row. To arrow.
R0. And
R0.
how much is T?
R0.
So this is 2. Okay, we're here. Oh man. So this is 1. So more or less we're here. So it's about 0.7. Okay, so remember that if this were a case with no influence of free surface, no influence from the frequency, this factor should be 1 because we are taking a circle. But because of the influence of the frequency, we have this little difference. Okay. Now, with this, we said that these three values, we can say that C is approximately equal to 0.7. Okay. So A33, it's C rho P B N squared over 8. So it's going to be 0.7. Density is 1025. This is seawater. Pi. The B is the diameter, which is 2. So it's going to be 4 meters squared divided by 8. So that's 2. So the result for me is 1127. And you can see that this is kilograms per meter. Okay, now we go on and calculate A33, large A33. And that's equal to, in this case, we assume that the section is constant. Okay, so it's a prismatic float. So this is simply this is the integration of A33 by simply A33 times L. So the length is 4 meters times this. will give us, my numbers are 4508 kilograms. Okay, now the mass, since you're floating up to half, it's going to be rho, that's the density of the water, half of the area by the length. So b squared over 4, that's the area of the full circle. If you divide it by 2, that's half. Times length and rho. So that's the mass of the float. You believe in me, that's going to be 6440 kilograms. Give me a couple of minutes, people. See, we're saying that we have this is floating, and we want to see that as a spring. Do you calculate this, the effective stiffness, people? Anybody remember? If you go up a little bit, how much buoyancy do you lose? Anybody?
The area of the water plane.
The water plane area.
Exactly, water plane area. So this is going to be BL times gamma. Please, this is specific weight. Okay, so it's going to be 2 times 4, that's meter squared. That's multiplied by 1025 times 9.8. That's Newton per cubic meter. According to my numbers, this is 80,360 newtons per meter. And now, finally, we can go back and see this is expression for omega 0 K over added mass plus mass. So finally, omega 0, it's 80,360 newtons per meters. Let me go back. 4508 plus 6440. So 4508 plus 6440, and these are kilograms. The result is 2.71 radians per second. So this is an approximation using the assumed value for the frequency. So we have to do a check. Okay, so we calculate omega 0 squared B over 2G. So it's going to be 2.71, the value that we have calculated, squared, times 2. That's the mass, the mean, 2 times G. Okay, so that's non-dimensional. And the value is 0.75. Okay, if we go back, we assume 0.4. So what we have to do is we have to iterate. Okay, usually one iteration is enough. So don't think that it is just too long. Okay, now in general, we don't do this calculation. Okay, what we do is we simply take the several waves okay, different length. And how are you going to identify the natural frequencies? People, how can you identify natural frequency? If you put some forces, some waves which are exciting the ship, how are you going to identify the values of the natural frequencies? Anybody? No? With the resonances, you can see there is an increment in response at certain regions, and about that, those are the resonance corresponds to natural frequencies. We have to be careful, and we will see this on Thursday's class, is because in this case, in ship dynamics, the excitation does not have a constant amplitude, okay? So according to the wavelength and wave frequency, the amplitude of the excitation is going to change. Okay, so we have to be a little bit careful. So the two natural frequencies, heave and pitch, they will be mixed together because they are close, and they said this is a problem because there is a change in excitation wave amplitude. But that's usually the way we do it. We don't do it like this. Okay, we don't calculate natural frequency directly. What we do is we calculate the response, and in the response, with these increments, resonances, we identify natural frequencies because this takes too much time. Okay. People, I already posted the next homework, the next assignment. You have to start right away. In general, according to our plans, remember, in 2 weeks, you will have to come back to Guayaquil for we're gonna do some tests in the lab, and also we're gonna give you the second evaluation. So we cannot waste any time, okay? The due date for this homework is on Tuesday. So you have 2 weeks for that. That's enough. I posted yesterday, so it's more than 2 weeks. So that's enough. You should be able to complete it on time, okay? Any questions?
Doctor, we have to go back to the university the first week of July, right? July
I don't remember
4th.
the dates. I don't remember the dates, but let me see. But yeah, in general, yes, that's in 2 weeks. Up to now. I know we have to be careful, yes. If something, yeah, that's the first week of July, yeah, Mr. Galarza. You're right.
All right, thank you.
Now, everything depends that in this, say in the next 10 days, our situation settles down, and if the authorities recognize that everything is going correctly with no potential problem for you, yes, we will confirm that you will have to come to the university in 2 weeks.
Right.
And yeah, we can play again, right? Because we need a revenge, right, Zamora? They beat us, but we're going to fight back. On that day, in 2 weeks, I'm going to have a team from faculty.
To play with who?
We're going to challenge you. Yeah. We can play Isaac, Ruben, and myself. And we can ask Nadia to come. So we're going to have 4. Be ready for us. Okay, people. See you Thursday. Bye-bye now.
Doctor,